Okay, I guess we can get the afternoon session started. Just a quick reminder at this time, we have 3 talks in this session. There'll be a little bit of a break before the 3rd talk, and immediately after the 3rd talk, we will have a reception across where we have the coffee breaks. All right, our first speaker for this afternoon is Sam van Leuven. He'll tell us about exact superconformal indices in closed form and BPS spectroscopy.
Okay, thanks a lot first to the organizers for inviting me and giving me the opportunity to talk and to have such a great workshop already. So my talk will be based on 2 recent preprints together with my master's student Kaylee Mattison and 3 postdocs at Wits, Pratik Roy, Advait Gaikwad, and Tanay Kibe. So the overall motivation is to study the nature of black hole microstates within the setting of ADS-CFT. Now, so far, lots of progress has been made in the counting of black hole entropy, especially, I would say, when there's an underlying 2-dimensional conformal field theory. But recently, this sort of counting success has also been extended to higher dimensional examples of ADS-CFT. But I think it's fair to say that the actual microstates are far less understood. And sort of the questions that arise there that Qiming also already mentioned is, does the dual to a typical heavy CFT state have a horizon? And if so, can we distinguish those states with a horizon from states that are smooth or horizonless? So as we've heard in the previous talk, there's now a sharp proposal, or a proposal for a sharp distinction between supersymmetric CFT states, dual either to smooth horizonless geometries or black hole geometries. And I won't be able to do any justice to it, but luckily we've had Qiming's talk here before. But the basic idea here is that if you consider a sequence of operators that are labeled by the central charge of the CFT, then the idea is that the smooth horizonless geometries would be dual to infinite sequences that will remain BPS for arbitrarily large n, and for that reason they are called monotonous. Whereas the black hole geometries would be dual to finite sequences, which become non-BPS at some critical value of n star, and those would be called fortuitous. And okay, the intuition that Qiming explained also is that when we have some fixed mass and charge, then a smooth geometry is expected to remain smooth as n goes to infinity or G Newton goes to 0. Whereas a black hole has a sort of sickness when we take n to infinity, as its area will go to 0 for fixed entropy. Okay, so the goal of this talk is to study this proposal in detail for the 4D NS4 theory. In this setting, then, it's believed that these 1/16 BPS fortuitous operators at strong coupling should become the microstates for BPS Kerr-Newman ADS5 black holes. And we're specifically interested in structural features and or patterns, if any, in the BPS spectra of these monotonous and fortuitous operators. So some examples that what I mean by that, by these features, is, for example, there was a proposal in the context of the supersymmetric SYK model that there's fortuitous operators somehow concentrate at a given R charge. That's what you could have in mind with these more structural features. Or what kind of dressings of fortuitous operators are allowed. For example, what monotone operators can I add to a fortuitous operator while remaining BPS? We've also heard a little bit about these Coulomb versus non-Coulomb operators. So Coulomb meaning that an operator is non-vanishing as you evaluate it on the Coulomb branch, on the Cartan. and non-Coulomb would be vanishing on the Cartan. And we also would like to understand if there's this dichotomy that now appears somehow to be there in terms of that monotone operators all seem to be Coulomb type, and fortuitous operators seem to be of non-Coulomb type. So how is that a strict dichotomy for depending on which, also depending on the gauge group? And the main tool that we'll use to study this is the superconformal index. So I'll very briefly introduce it also because I think many of the things here is really overlapping with Chiming's talk. So to introduce what the superconformal index is, let me first recall the NS4 superconformal symmetry. So we have the conformal group in 4 dimensions, R symmetry, 16 supercharges, 16 superconformal charges. And then a superconformal multiplet is labeled by a scaling dimension, 2 independent angular momenta, and 3 R charges. Now, to look at BPS operators, we pick a pair of super and superconformal charge. And then we consider their anti-commutator, which is this difference between the scaling dimension of the operator and the BPS energy, which is this combination of charges for these specific choice of supercharges. Now we call a multiplet short or BPS if every state in the multiplet has a vanishing small delta. And that's equivalent to the state being annihilated by both Q and Q dagger. By standard Hodge theory argument, BPS states, you can think of them as sort of harmonic forms. And then we know that these are actually in one-to-one correspondence with Q cohomology classes, meaning states that are annihilated just by Q modulo Q exact states. Okay. So again, I'm sorry for the repetition. I'll just try to go through it quickly. So the 1/16th BPS letters at 0 coupling in the NS4 theory, so just the fundamental fields, the ones that saturate this BPS bound is a component of the field strength, 2 components of the gaugino, 3 components of the chiralinos, and finally 3 holomorphic scalars. And there's 2 derivatives. And then any 1/16th BPS operator at 0 Yang-Mills coupling can be written as if these are the letters, then we write down a trace of a word. I guess these had to be inside, sorry. Okay. Now, as Chiming also reviewed, as one tunes the coupling, which we eventually want to do because we're interested in the strong coupling space of BPS states, well, then some of these short multiplets in the free theory, they may recombine into long multiplets and lift from the BPS spectrum. So the question is which states remain short or BPS at non-zero coupling? So there have been some approaches to this, and I mean, so far, this construction has mostly relied on a non-renormalization conjecture, namely that the BPS spectrum at one loop is not renormalized. And now the one loop BPS spectrum is equivalent to the classical or tree-level Q cohomology. So if this conjecture is correct, then the BPS spectrum at strong coupling would be in one-to-one correspondence with the classical Q cohomology. And that would be a way to approach this problem, at least to list the representatives of the strong coupling cohomology at weak coupling. Now, of course, we just heard that there is a counter example to this conjecture, but it's in a very specific context of this SO7 gauge theory. At the moment, it's not clear if that's something that is very specific to SO7 gauge group, which the kind of the argument that Chiming was giving with this dual Coxeter dummer, it might suggest that it could be something very specific for SO gauge theories. So perhaps this conjecture is true for SUN. It's just unclear at the moment. It won't play a very important role. Well, I'll mention when it becomes relevant. Okay. So then we have these monotonous and fortuitous cohomologies. So already back in 2013, all single trace monotone operators were constructed. And so how do you go about finding these fortuitous cohomologies? So I'm not really the right person to ask. There are many experts in the room that have actually done this, but I think if I summarize it correctly, the basic idea is, well, one approach could be that you consider this superconformal index that I have yet to define, and then because we have this sort of list of monotone operators, we can also construct a monotone, try to construct a monotone index, and then you can look at discrepancies between the full superconformal index and the monotone index, and that would give at least some hints if there are discrepancies where you should look for fortuitous operators. Okay, so let me finally define the superconformal index. So it's defined as a trace over the space of states on S3 of the theory, and then it's a weighted trace, including the -1 to the f, and some various fugacities that couple to the various charges in the theory. And it's designed in such a way that the contributions of long multiplets cancel, and therefore it's actually independent of the Yang-Mills coupling, and we can compute it exactly in the free theory. So how does it look? How does this computation look? Well, schematically, the idea is the following. So you actually forget about gauge symmetry. You just construct the full space of non-gauge singlets. You take the trace in that Fock space, and then to project onto gauge singlets, there is this nice trick that we can integrate over the gauge group, and that projects the non-gauge singlets onto gauge singlets. Okay. So explicitly for the NS4 theory, this expression then has the following form. So we have this projection, and then what you find here is what is sometimes called the single letter index. So these are operators that just consist of a single fundamental field with some arbitrary number of derivatives. And all these fields, as I said, they're gauge non-singlets. They live in the adjoint representation. So we multiply by the character of the adjoint representation. And then this plothistic exponential here, that's just a mathematical device that takes the single letter operators to the full space of multi-letter operators. Okay, now this integral over the unitary group is well known. You can write it as an integral over the eigenvalues of the unitary matrix. But you get a non-trivial measure here called the Haar measure in terms of the Vandermonde determinants. Okay, one thing that I want to point out is that while this expression is exact, it really manifests only the BPS spectrum of the free theory, right, by construction. So then you can ask a question, maybe a very ambitious question, but you can ask whether there exist alternative expressions for the index, which instead at least reflect some features of the BPS spectrum at non-zero coupling. So we're looking for some alternative closed form formulas for the index. Now, some things that may come to mind is, well, first, some of the things that have appeared in the literature before, some alternative expressions, is, well, first of all, you can just expand the integrand to some finite order, and then pick up the gauge singlets during the integral. That's a very simple thing to do. And then you will get the actual degeneracies, or really bosonic minus fermionic degeneracies of the strong coupling theory, right? But of course, that's not a closed form. That's only an expansion up to some finite order. There's also a formula that evaluates these eigenvalue integrals as a residue sum. That formula is known as the beta-ansatz formula. And it has some nice features. So for example, as shown by Benini and Milan, there's a specific residue in the sum that at large n has a nice interpretation in terms of the free energy, or the on-shell action of these supersymmetric black holes. So there's a specific residue that dominates the residue sum at large n. We've also heard this week about the giant graviton expansion. I should say maybe there's also some, so the beta ansatz has some nice features, but also some less nice features. So in particular, it's the full classification of all the residues is not fully understood. So it's sort of an indirect or implicit expression in that sense. We've also heard about the giant graviton expansion earlier this workshop, which is also some kind of closed form for the index, but it really reflects features of the gravitational theory. In terms of the gauge theory, it might not be a very, it's not perhaps not the most useful expression in that it includes various ghost contributions and such. And then, I listed finally also, there's also a TQFT formula for the index, where the index is expressed as some correlator on a Riemann surface, but also that is not very obviously connected to the question that we're asking. Okay. So in the remainder of this talk, I want to provide an alternative approach to evaluating these closed form formulas for the index. Like the beta ansatz, it evaluates these contour integrals through residues, but it's a different way of approaching the problem. And then discuss how the resulting expressions reflect features of the BPS spectrum at non-zero coupling. Okay, maybe I should just pause if there's any questions. Okay. Okay, so I'm gonna do this in steps. So I'm gonna show how to evaluate this residue sum for increasing levels of complexity. So we're gonna start with the whole Littlewood sector. So recall that the index is a function of 4 parameters. And the simplest and the highest degree supersymmetric sector here is the sector where you take P and Q to 0. And that captures the so-called 3/16 BPS as Hall-Littlewood sector. Then we're going to look at the 1/8 BPS sector, sometimes called the Schur sector or the McDonald sector. And then finally, we'll go to the full superconformal index. Okay? And I'm going to look at all these indices in turn for just the very simplest possible gauge group, namely SU2 gauge group. Okay? All right. So let's start with the Hall-Littlewood index. So in this case, you can check that the contributing letters are 2 scalars and a single chiralino, single fermion, and no derivatives. Okay, so I can just construct the index, and the integral over SU2 is just a single contour integral where the contour is a unit circle. And in this case, the integrand is just a rational function. So it's very straightforward to calculate this by residues. We just we list the poles inside the unit circle. We pick up the residues using Cauchy's theorem. And after some simplification, we obtain the following expression. Okay, that's... now, what is the interpretation of this expression? Well, we can see the traces of various protected operators that are known to be protected. So we have trace x squared and trace y squared. Those are the chiral primaries, trace xy. And those are clearly reflected. So trace x squared and trace y squared are clearly reflected in the denominator here. The fermionic operators here, x psi and y psi, are clearly reflected here. The minus sign is because of the minus 1 to the f. And then finally, this other bosonic operator, trace xy, appears in the numerator here, not in the denominator. So you might ask, why does it appear in the numerator? Why can't we have arbitrary powers of it? And you might have also asked where, in principle, this should also be a single trace operator that you would have expected to enter. But we also don't see this guy. And this is explained by a lifting phenomenon. So when G is non-zero, right? So this is certainly an independent BPS operator in the free theory, but when G is not equal to 0, we have the following phenomenon. So it turns out that the square of this trace xy, taken together with this guy, through an SU2 trace relation, is related to trace of a commutator of x and y squared. And this commutator is actually Q exact, okay? With this missing or absent operator. So here we see an example of a lifting where the xy squared contribution actually pairs up with this operator and lifts from the BPS spectrum as we turn on the copy. And in fact, this is a known thing. So trace of x commutator y squared is a superconformal descendant of the Konishi operator, which is well known to lift at one loop. The upshot here is that the whole Littlewood index is fully captured by monotonous operators. Okay, so there's no sign of fortuity here. Okay. Okay, so that was very simple, but just as a warm-up. Now we get to the McDonald index. So in the case of the McDonald index, we still have the two scalars, x and y, and the fermion, but now also a component of the gaugino contributes, and an infinite tower of derivatives. Okay, so as a consequence, now we have an infinite product in the integrand, both in the numerator and denominator, which just signifies, so these are so-called infinite Q-Pochhammer symbols. That's just an infinite product like this, and just captures all the derivatives, the infinite set of derivatives of these operators. So you might ask, can we evaluate this integral, now again by residues? So, well, it turns out that integrals of this type are very well studied in the mathematical literature. So mathematicians have considered, there are books written about this. Mathematicians have considered integrals of this type, in fact, even a little bit more general than this. But you see here, this is some set of Q-Pochhammers. So here we have 2n Q-Pochhammers in the numerator. I've just used the notation where I don't keep writing the Q infinity all the time. So different commas here separate different Q-Pochhammers. And we have this, okay, we can consider integrals, mathematicians have considered integrals of this type. And so how would you go about doing it? Well, you first have to list the poles inside the unit circle. So in this case, the poles are coming inside the unit circle, are coming from these Q-Pochhammers here. And we see that they appear in infinite towers, okay? And these pole towers, they accumulate, because the absolute value of Q is less than 1, these pole towers accumulate at the origin, okay? So that's actually a key technical, that turns out to be a key technical difficulty. It means that this potential singularity at the origin is non-isolated, because there's an accumulation point of poles. And as such, we can't really isolate it. We can't isolate its contributions. We can't really evaluate how it contributes using Cauchy theorem, for example. Okay. Okay, so ignoring that for the moment, so let's just look at the residues associated to the poles except the origin. So mathematicians have shown, and that's really an easy exercise to show, that given these conditions here, it's easy to show that the residue at a given pole here will contribute at some order in a small Q expansion, at some order zeta to the power k, where zeta is related to the parameters that multiply S inverse here, okay? So in particular, we have this infinite sum of residues where the kth residue is suppressed by zeta to the power k. So this, ignoring the contribution of the origin, the residue sum will converge if zeta, absolute value zeta is smaller than 1. Now, what about the origin? So how should we think about the origin? So let me define a contour CK, which sits, let's say, in the kth annulus Okay, so I've here drawn it this green. So here each dashed line would be a step of Q, and then this green contour CK, we put it somewhere between the kth and the kth plus 1. The kth annulus. Okay. Now, what you can show using the Cauchy-Schwarz inequality and the similar manipulations as before, what you can show is that the contour integral on CK is bounded, the absolute value of that contour integral is bounded by the integral over the contour CK and then the absolute value of the integrand. That's just Cauchy-Schwarz. But now, if we plug in, if we plug in the value of S on this contour, which is the absolute value is given by Q to the power K, you can figure out, using essentially the same manipulations as on the previous slide, that again, this will be this contribution will be of order zeta to the power K. So, as we take K very large, this contour will wrap the origin increasingly tightly. And because it's ordered zeta to the k, we see that if the absolute value of zeta is less than 1, then this contribution at the origin can essentially be argued to vanish. Okay? So somehow the convergence of the residue sum associated to the poles except the origin, the convergence of that residue sum is closely tied to the vanishing of a contribution of the origin. All right. Now, of course, in our case, we are out of luck because you can calculate this zeta. Remember, it was related to the parameters in the integrand. So we can just calculate it. It's related to the parameters multiplying S inverse. We can calculate it, and it's equal to 1. Okay? So that means that the residue sum associated to all the poles except the origin would diverge, at least naively diverge, and relatedly, there would be a non-vanishing contribution from the origin. But again, as I said, we can't apply Cauchy theorem to the origin, so effectively, we can't really make sense of the residue sum. Okay. Now, there's an observation. So if we stare at this integral, well, actually, part of what appears in the numerator, if I factor that out, that was actually the Haar measure that I was telling about. So I've just factored out 2 factors from this Q-Pochhammer to make that explicit. So there's the Haar measure associated to the integration over SU2. And now there's a very elementary fact that the integral of this, for a function that is the same as you exchange S and S inverse, which is true for this integrand, it's a very elementary fact that this half times the integral with the full Haar measure is equal to just the integral with 1 part here of the Haar measure, integrated against the rest. Okay? Okay, this observation is completely elementary. But this generalizes to SUN integrals. It generalizes to higher rank. And the interpretation actually of this is that, well, once we've written the integral over the unitary group as an integral over eigenvalues, that integrand still has a remaining gauge symmetry, residual gauge symmetry, which you can think of as the Weil symmetry. And this alternative form of the integrand is just fixing that symmetry as well. That's how you can think about it. But now, that means that we have an equivalent integral. So I can do this replacement in the integral of interest. And you see there's now an imbalance here between 2 of these Q-Pochhammers, which gives us a value of zeta which is not equal to 1, which is now equal to Q, which has absolute value less than 1. So in this case, given this fact, we have argued in general that now the residue sum associated to the poles outside excluding the origin will converge, and the contribution of the origin vanishes, and we can make sense of the residues. Okay, so let's apply that and then calculate the McDonald index for residues. And after some massaging of the resulting residue sum, you get the following expression. So it looks like this. So we have some prefactor, and then an infinite sum. Okay, and now this prefactor has a nice interpretation again. So the prefactor, you can think of again as protected operators, in terms of protected operators, in particular, more specifically monotone operators, namely these guys. So I've sort of color-coded them. So there's the trace x squared, trace y squared, and two fermionic operators, and their derivatives. That's what the infinite products here reflect. And it turns out that you actually, what is special? You might ask what is special about this specific set of operators. Well, it turns out that these guys generate a maximal free subring in the full ring of monotones. So in particular, there are no trace relations among these operators. Okay, so it kind of makes sense that they appear as sort of a free prefactor in the index. Okay, so what about this? What about the sum? Well, there are additional monotone operators, additional protected operators in the 1/8 BPS sector. They're given by these guys and their derivatives. And yeah, you can sort of convince yourself that these are indeed somehow encoded in this sum, which, by the way, is this is a special function that is known as a basic hypergeometric series or a Q-deformed hypergeometric series, free phi 2. Yeah, so somehow the additional generators plus then the relations that these operators satisfy amongst themselves is sort of remarkably efficiently encoded in this basic hypergeometric series. Okay. And in particular, the upshot here is that, again, there are no signs of fortuitous operators. So I don't claim that I fully understand, by the way, this expression. So that's still something open. But it seems that this closed form, at least maybe a little bit more work, could be used to show that there are no fortuitous operators in the McDonald sector, if we can fully understand this expression in the combinatorics in terms of the McDonald sector. Okay, and that is consistent. Yeah.
For individual sum.
Sorry.
Do you have interpretation for individual sum for each k?
For a summand, you're asking. Yeah. No, I don't at the moment. I don't at the moment. Yeah. But but that is exactly what I would like to. Yeah, that's exactly the question. Yeah. Okay. This is this, by the way, is consistent with various other works in the literature. That there's no that the monotonous or operators fully comprise the McDonald sector. Okay. Now, let me just mention some other benefits of this closed form. So the fact that it's written in terms of a special function, this basic hypergeometric series, these are studied in lots of detail in the mathematical literature. And in particular, they satisfy many, many identities. And those identities you can use, actually, to arrive at different forms that might also have interesting interpretations. Also, the closed form expression manifests various mathematical properties of the index, including analytic properties in the fugacities. Okay, we'll leave it at that. Okay, so now this basic idea of replacing the full Haar measure with what we call the reduced Haar measure. You can actually also show that the residue sum associated with the full 1/16th BPS index can be evaluated. So you can argue that the residue sum is convergent and that this contribution of the origin, which for the normal contour integral expression for the full index would be problematic, you can actually argue, essentially because of the convergence of the residue sum excluding the origin, you can argue that this contribution at the origin would vanish using this reduced measure that I was talking about. And if I do that, and I evaluate the residue sum, it takes on this form. So, okay, this is a complicated form, so let me unpack it just a little bit. I'm not going to spend too much time on this expression, but there are some reduced Jacobi theta functions that appear. There are elliptic gamma functions that appear. And then finally, there are also what are called, there are traces of elliptic hypergeometric series. I should be a little bit more precise. These are actually the summons of what are known as elliptic hypergeometric series. And there's this funny denominator that actually is closely related to working with this reduced higher measure. Okay. Anyway, this expression is still a bit complicated to interpret, but let me just point out two things. So this is an alternative. So the beta ansatz approach also allows you to obtain a closed form residue sum for the SU2 index. But the beta ansatz expression only holds for when P and Q are related in a certain way. This expression is somehow complementary. So this expression only really makes sense when P and Q are not related in the beta ansatz. So in some sense, I wouldn't call it more general. It's somehow it's valid in a complementary regime. Okay. Now it also has, the formula also has some strong similarities with so-called Higgs branch formulas. But let me also not spend on it. So this formula, for now, we haven't been able to simplify this formula into a form that maybe into a form that allows an interpretation similar to what I gave you with the MacDonald or the Hall-Littlewood index. So that's still an open problem, or it might not even be possible. I'm not entirely sure. I'm not sure. Okay, so maybe to sort of summarize. So far we've been able to find some closed form expressions for the index, but sort of for the most interesting case, where fortuitous operators appear, we're not really able yet to interpret this in terms of the spectrum and maybe learn something about the BPS spectrum at non-zero coupling, which is what we were trying to do in the first place, right? So how do we proceed? Now, it turns out that there is a certain refinement possible of the superconformal index. Namely, at one loop, the one loop spectrum of the one loop BPS spectrum. At one loop, there is an additional symmetry that was found by Qiming, and this is sometimes called the U1Y bonus symmetry. And here, the charge associated to the symmetry just counts the number of letters in an operator. And you can check that the tree-level supercharge increases the number of letters in an operator by 1, and the superconformal charge decreases by 1, so that the one-loop Hamiltonian commutes with this charge. And you can use this symmetry to refine the index. So we include an additional parameter z, and we include this charge y in a specific way. And we have sort of defined this way a refinement of the superconformal index. It reduces to the ordinary superconformal index for when z is specialized in this way. Okay, and the price to pay for this refinement is that this object is really only protected. So this symmetry doesn't persist to higher loops. So the price that you pay is that you really defined an index that is only protected from the free theory to the one-loop spectrum. But it's still some protection, right? And in fact, if you assume the one-loop conjecture, that is even a very powerful object still, if nothing renormalizes beyond the one-loop spectrum, okay? And of course, in this case, having an additional fugacity, there's a much richer set of letter-based truncations than just this whole Littlewood, MacDonald, and 1/16 BPS sectors. And we can study these more interesting sectors, which can be viewed as closed subsectors under the action of the tree-level supercharge. Okay, so the refined one, the fully refined one-loop index is given like this. So it's very similar to the full superconformal index, but we have 5 parameters. It depends on 5 parameters now. Now, we can again consider the limit where P and Q both go to 0, which was this particularly simple case, in which case the integrand reduces to a rational function. We don't have to worry about these complicated residue calculations. Unlike in the whole Littlewood case that I discussed before, in this case, Z can be kept fixed. Otherwise, we would have also had to take this parameter Z would also go to 0 in the normal superconformal index. And then we get a much larger set of contributing letters. So this index, by the way, was introduced in these papers. And okay, and so that's a more interesting sector in which you can calculate the index. Right. So the integrand now in this P and Q to 0 limits is a rational function. So it's easy to obtain a closed form expression for the BMN index. But we want to do a little bit better. We want to not just calculate the full superconformal index, but we kind of want to separate out, we want to subtract off the monotone index to get some idea of the fortuitous spectrum. Okay? So to subtract off the monotone index, we need to understand the spectrum of monotones, and that's actually a little bit more complicated. But okay, so it turns out that the BMN monotone operators are given by sort of 3 types of, the single trace ones are given by 3 different types of single trace operators. So we have the chiral primary, and then level 1 and level 2 descent. And here, because of trace relations, the number of letters inside a trace, we restrict it to be less or equal than n, where n is the rank of the gauge group. Sorry, where n is the SUN. Here, also note that these upper indices here, they actually, so this 1/16 BPS sector transforms under a subgroup of the R symmetry, and SU3 are a subgroup. And upper indices indicate fundamental, and lower indices anti-fundamental SU3R indices. Okay. Now, okay, so I've given you the single trace operators, but if we want to calculate the index, we need to, build the full space of states. That we also need to consider multi-trace operators, and then at finite n, the computing that index is complicated because of trace relations. And as it turns out, the only explicit expression, the only full construction in the literature that is available is for SU2 gauge group. Now, to simplify, we'd like to do better. We'd like to go to higher rank, and to simplify the construction of the monotone index, we're going to restrict to singlets under this SU3R symmetry. That is equivalent to setting all these R charges equal. Now, the nice thing about this sector is actually that it's non-trivial. In particular, it contains fortuitous operators, including the threshold cohomologies, so the first examples of fortuitous operators for both SU2 and SU3 gauge group. And even this higher loop lifting example that Qiming told us about, that also occurs in this SU3R singlet sector. So the 2 operators that pair up at 2 loops, they are both SU3R singlets. So it seems like a lot of the sort of rich and interesting physics of these BPS operators is still present in the SU3R singlet sector. Okay? But it allows us to simplify the computation of the monotone index. Okay, so how do we proceed? So now we still need to consider constructing this full set of multi-trace operators, modulo trace relations. But in addition, we want to form SU3R singlets, which means that we just have to contract all the indices, all the SU3R indices of a multi-trace operator. We can do that with the epsilon or the delta tensor for SU3, the invariant tensors for SU. And now, sort of luckily in a way, but there's some luck, is that it turns out that this explicit construction is very easy to carry out, at least at low rank. The reason is that it actually turns out that for SU2 gauge group, you cannot construct any monotone operator that is a singlet under SU3R. So the monotone index trivializes for SU2 gauge group. And for SU3 gauge group, it truncates at some finite order. In fact, there are only two non-trivial monotone operators that you can construct that are singlets under SU3R. For SU4, we haven't done the calculation exhaustively, but we've found that for SU4, there does appear at least one infinite tower. So there is, in fact, one bosonic singlet that is a monotone operator that you can construct. And okay, we haven't fully carried out this calculation. Yeah, so in particular, note that in SU3, it turns out that the only singlet monotones that you can construct are fermionic, and that's the reason why this index truncates at finite order. Okay, so let's see how I'm doing with time. Okay, so maybe I can give a little bit more detail on that. So if we want to understand where this is coming from, well, for SU2 gauge theory, we can think of the monotone operators. We can think of them in terms of the eigenvalues of the matrices, and then the monotone operators have to have an even total number of these degrees of freedom in the specific combinations that they appear in the chiral primaries and the descendants. The reason why you find this one is, well, you can't find any bosonic singlet because there's only 3 bosonic eigenvalues here. And, well, clearly the only way to contract these is using an epsilon tensor, but the bosonic eigenvalues are symmetric in these indices, whereas the epsilon tensor is anti-symmetric. So you can't create a purely bosonic singlet, SU3R singlet. And essentially similar reasoning applies to the sectors that include fermions, and we can only go up to 3 fermions because there are only 3 fermionic eigenvalues. Okay, so that's essentially how you can arrive at this value for the monotone index, this trivial value. Okay, one can do something similar for SU3 gauge group. The singlet monotones that you find, they have their indices contracted in this specific way. Okay, maybe the details are not that important. The important thing is that these are these are all fermionic. Okay, so we can't. That's the reason that this thing truncates at finite order. Okay. So that is we've constructed now the monotone index. To calculate the full index in the SU3R singlet sector, we just organize the integrand in terms of SU3R characters as well. So we have the gauge symmetry character, but now also the SU3R characters. So here are the scalars in the fundamental representation. Here are the fermions in the anti-fundamental representation, and finally the field strength. And we just not only integrate over the gauge group, but we also integrate over SU3R. And that gives us the projection of the full index onto SU3R singlets. And then finally, we can write down the index over the fortuitous part of the spectrum. So how does the index look for SU2? It's a closed form for SU2. And it looks like this. So what do we see here? Well, this minus t to the 24, it reflects the so-called threshold fortuitous cohomology that was constructed in these papers. It's a fermionic operator. Now, the denominator here reflects a dressing by, these are not monotonous operators, so it reflects a dressing by the trace of the field strength squared. I'm putting this twiddle here because you actually have to make this Q closed. There have to be some terms in addition. You have to add some terms here to the operator to make it Q closed. But the essence of this infinite power is due to a dressing of the fortuitous operators with trace F squared. Okay. Then what do we find at t to the power 30 and t to the power 36? So you can create a superconformal descendant of the threshold cohomology that is also a singlet under SU3R. So these are some supercharges that commute with our choice of supercharge. We can use it to get another singlet that sits in the superconformal multiplet of this fortuitous operator O0, and similarly for all the On. And then as it turns out, okay, these are maybe too many details, but it turns out that you can also form a non-vanishing singlet by acting with just two supercharges and adding a monotone hair, if you want, to these On operators. Okay, we can carry out the procedure also for SU3 gauge group, and you get the following closed form for the fortuitous index in the SU3R singlet sector. And yeah, so this is somehow what we were after. So we have a closed form expression for an index that really teaches us something about how the fortuitous spectrum is organized. At least in this SU3R singlet sector. So in this case, we again see a denominator 1 minus t to the 12, now also 1 minus t to the 18. So these can be identified by these dressings with trace f squared or trace f cubed in this case, up to corrections that you have to add to the fortuitous operator to make it Q closed. Okay, and maybe some other features that you can observe from this expression is that it appears that the first operator that appears is at order t to the 24, but then the second one that appears, modulo these dressings, is only at t to the power 18. So there seems to be a bit of a large gap between the threshold operator and the next fortuitous operator. So that hopefully that can be understood. Maybe it suggests that there are no descendants of this threshold cohomology, or maybe it can't be dressed for a reason, for some reason. And then we find that you can also observe that there are many gaps of order t to the 6, and that can also be explained in terms of for example, superconformal descendants that are again singlets under SU3R. Okay, so let me conclude. So the residue evaluation of the superconformal index, it can be made sense of using this reduced Haar measure. You can get a convergent residue sum. You don't have to worry about this nasty singularity at the origin. And it can serve as a useful intermediate step to arrive at some closed form expression for the index that at least encodes some features of the BPS spectrum and non-zero coupling. At least I hope that I've convinced you of that. In some cases, we've used it to deduce some structural features about the spectrum of fortuitous operators for the NS4 theory. Now, some future directions. So it would be very nice to either have a simplification or interpretation of the residue sum that I presented for the full superconformal index, because that's clearly the most interesting object. In particular, given that we have this, we've done away with the integral, and we have sort of an expression that reflects also certain analytic features on of the dependence of the index on the various fugacities. Perhaps there is an application of this formula to, for example, the gray galaxy instability studied by some of the people in this audience. Now, the generalization to larger values of n is in principle straightforward. So this reduction of the higher measure that allows to calculate the residue sum, that extends to higher rank. It just becomes messier because there's just the number of poles that you have to take into account becomes larger very quickly. So it's messy, but it's possible. There's no obstruction to carrying out this calculation in principle. If you saw the expression, for example, that I gave you for the McDonald index, it had this form that is a bit similar to the form of the giant graviton expansion. It's not the same, but there's some similarities. You have this sort of prefactor. In our case, it reflected sort of the maximal free subring of the set of operators, and then you get a series form that somehow implements, well, in our case, additional generators and relations, and that's also something that at least naively sounds a bit similar to the giant graviton expansion, where the sum here implements trace relations. So there's some similarities. Now, another direction that I think is very interesting and important is the status of the one-loop conjecture for SUN, say. So for SO7, we know that there are at least some operators that lift at higher loops. So it's really, I think, an important question to figure this out, what the story is for SUN, because that also has implications for the interpretation of the BMN index. Because the BMN index is really only protected from the free to one loop. If you somehow have to, the interpretation in terms of fortuitous operators sort of relies on this one loop conjecture. So one should really figure out if it still holds for SUN. Okay, and then finally also this sort of observation that the monotone operators in the singlet sector can almost completely factor out. There's very few monotone operators in the SU3R singlet sector, while there is actually the infinite towers of fortuitous operators remain. That also, I would also like to understand better why that is the case. Okay, let me leave it there. So thanks for listening.
Questions?
So if you restrict to the SU3R singular sector, do you know if you still have e to the n squared growth of number of states?
I haven't checked that. That's a good question. I mean, it's a bit hard to check this, I guess, at the. So you're specifically you're asking about just the full index, I guess.
Or BMN. Yeah.
BMN index, but not necessarily.
Try to answer both questions.
Yeah. Okay, it's something we haven't checked, but that should be easily possible, I guess, to check. Yeah. I'm not sure. Yeah, that's an interesting question. Yeah.
Just a comment to complement what you said about the McDonald sector.
Yeah.
We have computed the McDonald SU2 monotone index up to 72 order, and there was no fortuitous operator,
Okay, I
as
see.
you said.
I see. Okay, yeah. Thanks.
So is this technique useful for for example, going to the microcanonical ensemble by doing further contour integrals with respect to fugacity? Could it be that if you do something like that and go to some kind of large charge, could it be that it further simplifies?
Yeah. So, well, what do you have exactly in mind? That.
Well, maybe just a general question, is this useful for going to the microcanonical, right? Fixing the charge rather than
But
fixing
you
the charge?
mean, but what is useful? Just
This technique of integration?
but I'm okay. But it's in that case, so in that case you're not really integrating over a group, right? So you do an inverse Laplace transform with respect to P or Q, perhaps, is what you have.
Yeah, but combining this with what you did for the group, and then just a big general question.
Yeah. I mean, if you're asking if this method that I introduced is useful for that, I don't think that method is maybe necessary in that case. Although I think from Ji-Hoon's talk, actually, he does also get these accumulation points of poles. I think, but in that case, they're not located at a single point, but he finds whole walls of accumulation points.
I guess maybe I'm just asking whether the final expression that you got, is this used for going to the fixed charge?
I see. I'm not. It could be in the sense that it's maybe yeah. So let's see. So I guess one of the useful features of these closed form expressions is that they manifest the analytic dependence on the fugacities. So you can indeed imagine that it would be easier to do this inverse Laplace transform, maybe deform the contour over the sphere and then start picking up poles in Q, for example. Yeah, then I guess this could be a useful expression indeed. Yeah.
All right, let's thank the speaker again.